Okay, dear students, today I am going to discuss Ampere circular law. So this is given by Ampere. It relates the magnetic field and current. So consider an open surface with a closed boundary. Okay, it's a closed boundary is there, but surface is open. Now there is some current I enclosed within that surface and flowing through the surface. Current I is there, and then magnetic field B. Magnetic field B at every point is different on the surface. So the magnetic line integral of magnetic field and the elemental length, that is B dot dl. Line integral of magnetic field and elemental length dl over a closed loop, okay, is equal to mu naught into I. This is the Ampere circular law mathematically. Integral of over a closed loop B dot dl equal to mu naught I, where I is the current enclosed within the surface or within this loop. Okay, so I is the current, total current. If some currents are flowing that way, some currents coming this way, and net current we have to take here as I. Okay, and where mu naught is equal to 4 pi into 10 power minus 7, okay, Henry per meter. This is the constant of proportionality. So what you have to do is, at every point on this surface, magnetic field B and the elemental length, small length dl, and if you take the dot product, what is the significance of dot product? B dot dl equal to B into dl into cos theta, angle between magnetic field at that point and the dl vector. So that cos theta we have to take. So now if B and dl are parallel in the same direction, then cos theta is 1. So B dot dl becomes just B into dl. So at every point we add the product B dl, and over the entire loop we add the this one process, and we get that is called as line integral. This is the integration symbol. Integration means simply it is summation. Okay. So here summation is over the entire loop or entire surface. From one point we start, entire loop we cover and come to the same point. Then the B dot dl summation is over. So that B dot dl at every point on the surface added up to get complete over the loop, that is equal to mu naught is a constant multiplied by the net current enclosed within the surface. Now this Ampere circuit law is useful in finding the magnetic field in different situations. So firstly, magnetic field due to infinitely long straight conductor we find out. Then we will go for solenoid, then toroid. So this is the mathematical meaning of or mathematical equation of Ampere circular law. That is the line integral of, I repeat the statement, the line integral of magnetic field and the elemental length over the entire loop, means LHS, is equal to mu naught times the net current enclosed within the loop or enclosed within that surface. So mu naught I. So this is all about the Ampere circular law statement, and equation you explain, state and explain Ampere circular law means you have to write the statement. The line integral of magnetic field B and the elemental length dl over entire loop is equal to mu naught times the net current enclosed in the loop. That is statement. And then this expression is the explanation, and right, B is the magnetic field, I is the current. This is about the state and explain Ampere circular law, and draw a small diagram. And then is the application or use of this Ampere circular law for finding the magnetic field due to a infinitely long straight current carrying conductor. Okay. So straight current carrying conductor, I will take for sake of convenience upward current is going this way, and magnetic field at any point, at a point P, I have to find out the magnetic field at this point. Okay, at a point P I have to find out the magnetic field. So what I will do, I will take the distance as r here. Okay, this distance equal to r, and I will construct a circular loop with this point as center here. Okay, this is the center here, and this point P is on the circumference of that circle. I imagine such a circle now. Okay, I will draw that as an Amperian loop. Okay, so this is the Amperian loop like this. Okay, this is the Amperian loop. Now at this point P on the Amperian loop or in that circle, I will take a small elemental length. Okay, B dl, and the magnetic field is also in the direction same as dl vector. Okay, so here in this in this point P, the magnetic field B, I said in the earlier classes, if a straight current carrying conductor is there, magnetic field lines are circular. Around the conductor, magnetic field lines are circular. This is the conductor carrying current upward. Suppose the magnetic field lines are circular closed loops, and at all points on that circle, the magnitude of the field should be equal because the distance is same and the source is nothing but current, which is same. By symmetry, we can say at all points on the circumference, means at one circle magnetic field is same. If you go a little outer circle, then magnetic field decreases because magnetic field decreases as the distance increases. As the distance increases, magnetic field decreases. So let at a point P the magnetic field BB, and the small elemental length on the circle I will take as GL, and R with the distance of that point P from the conductor. Okay, so now this is the diagram, a small diagram you have to assume like this. Okay, like this, we assume a small diagram. Okay, now current I have shown, and R is the distance of the point from the center of the loop or the conductor. Okay, so we assume a Amperian loop as a circular loop. Now according to Ampere's circuit law, what is given? Line integral of B dot dl. We have to write this. Line integral of B dot dl equal to mu naught I. Okay. So this loop consists of one current here, one conductor is there, infinitely long conductor. So I have to extend both the sides with the dotted line. Infinitely long straight conductor which is carrying a current I. And the direction of the field, you see, hold the conductor in your right hand, so that the curled fingers around the conductor show the direction of magnetic field. So magnetic field lines are circular here, everywhere it is there on the outside the conductor. And according to this Ampere circuit law, or from Ampere circuit law, we can write like this. Okay. Now what I am doing is magnetic field due to infinitely long, this is important derivation for 3 marks. Magnetic field due to infinitely long straight conductor. Long straight conductor carrying current. Straight conductor carrying current. So this is the derivation for 3 marks, that is using the Ampere circuit law. So one diagram is compulsory. Now using Ampere's law, and from Ampere's law we can say that mathematically B dot dl equal to mu naught I, where I is the current through the conductor. I is the current through the conductor. Okay, fine. Now what we have to do? Take a small portion here dl and B as the magnetic field. Now what is that B dot dl? Let me find out first B dot dl. Dot product or scalar product of magnetic field at the point P and dl vector. So that is B into dl into cos theta. So but here see theta, I said magnetic field is into the plane of board here and dl also into the plane of board. The elemental length and the field are parallel or coinciding, you can say. So in such case the theta value is 0. Theta value is 0. So that means it is B dl into cos 0. Okay, so b dl cos 0. Okay, so that is b dl. It becomes b dl. So cos 0 is 1. Okay, when cos theta is cos 0, the value of cos 0 is 1. Okay, so b dot dl is just b into dl, as cos 0 is 1. Now line integral is there. Okay, so line integral, then we go back to this b dot dl, we find out this, that is integral of b dl. Now what is the special thing? Magnetic field B at every point on the loop is the same value. Magnetic field has the same value at all points. Why? Current is same. This current carrying through the conductor is same. Okay, current is same, and the distance r, it is circular loop I assumed. Amperian loop is circular loop here. So the current same, distance same for all the point on this circular loop. Hence the magnetic field value is also same. At all points the magnetic field is same. So then we can take the b value. Whenever it is constant, we can take outside the integration or differentiation. You not do any integration or differentiation for the constant. If it is variable, you have to use the product rule. But here it is constant, so take out. So b outside. Then summation of integral of dl. Now what is integral of dl means? So small dl, then another dl, another dl, another dl, another dl. I have done in the circular loop. Magnetic field due to a circular loop carrying current I discussed. So same way here, adding dl, dl, dl on entire loop. We assumed one Amperian loop. So what is the length of such Amperian loop? Or summing of this dl over the entire loop? That's what we have tried. So okay, so line integral b dot dl is nothing but 2 pi r. Okay, 2 pi r. That is the circumference of the loop. That means you are adding a small elemental length, again a small elemental length, another dl like that. For the entire loop, completely you are adding all dl values. So when it may be 1 millimeter, 1 millimeter, 1 millimeter. If you add 1000 times, it becomes 1 meter. The same idea. However the small the elemental length may be, but when you add up the entire loop dls over entire loop, closed loop, you get 2 pi r. That is circumference of the circle. So then it becomes b into 2 pi r. Now we got line integral b dot dl equal to b into 2 pi r. So this Ampere circuit law I will choose as equation 1. Now using in 1. So using in 1 what happens? Using in equation 1, b dot dl equal to b dot product, it is b into 2 pi r. Correct? So LHS is b into 2 pi r equal to mu naught I RHS equal to mu naught I. Okay, so then what happens? B into 2 pi r equal to mu naught I means I get the expression for b. So b equal to, take 2 pi r into other side. So it is mu naught I divided by 2 pi r. Mu naught I divided by 2 pi r. What it indicates? B is the magnetic field. The magnitude of magnetic field at a point B at a distance r from a straight infinitely long conductor carrying a current I. This is the magnetic field due to infinite long straight conductor. So in the previous class I have discussed, I have derived the magnetic field due to a circular loop, and hence I found the magnetic field due to a circular coil of N turns. Here I find the magnetic field due to infinitely long straight conductor carrying a current I. It is a straight conductor. We find the magnetic field around it at any point P at a distance r from the conductor, and we assume Amperian loop as a circular loop. So this is the Amperian loop. Just for the sake of derivation, we assume an Amperian loop. Okay, that is circular loop. So this is the expression for the magnetic field due to the straight conductor carrying current, infinitely long straight conductor. Okay, so based on these questions can be asked here, that is find the magnetic field due to a current carrying wire. Okay, current carrying wire carrying a current of say 100 ampere, carrying a current 100 ampere at a distance 2 meter from it. 2 meter from it. Okay, so we can see the current carrying wires. Okay, so what is the magnetic you have to write the formula. Okay, 2 pi r. Substitute. Mu naught is 4 pi into 10 power minus 7. Okay, into current I. Current is here I, 100 ampere. Okay, so 100 ampere, 100 divided by 2 pi into distance r. It is 2 meter is the distance given. Correct? Yes, 2 meter. So now what happens? 2 pi into 2 is 4 pi, and this 4 pi cancels. 100 remains. So 10 power minus 7, here 10 power 2. So 10 power minus 5 Tesla. And the unit of magnetic field B is Tesla. Hence the magnetic field will be a straight conductor carrying a current of 100 ampere at a distance of 2 meter from it here. Okay, so the magnetic field value B is this much, and it is into the plane of board if the conductor is horizontal, field is inward. So it is a circular loop. We have to use the right hand rule to find the field. Okay, so current is flowing like this. The magnetic field, okay, magnetic field will be inside, it is coming outside, like this it comes. And the magnet of magnetic field is 10 power minus 5 Tesla. At a distance of 2 meter means 10 power minus 5 Tesla. So this is about amperes, using ampere circuit law, obtaining the expression for a magnetic field due to current carrying straight conductor. Okay, that's all. Then I go to the next topic, that is solenoid and toroid. These two devices which are used to find the magnetic field. Solenoid and toroid are the two devices which are used to find the magnetic field, or I mean to produce the magnetic field. They produce uniform magnetic field. Okay. Firstly, solenoid. Solenoid is used to produce uniform magnetic field. So how is the solenoid? Solenoid means it consists of a cylindrical tube on which the cylindrical tube large number of insulated copper wire is wounded, very closely wounded. Okay, and this is connected to some battery. Okay, like this. Okay, now we can put a switch here. Okay, now when switch is closed like this, the current flows in this. Okay, so current flows like this. So when current flows through this, what happens? There will be magnetic field produced by this solenoid. So magnetic field produced by this solenoid will be like this. Okay, so magnetic field is produced, schematically represented this way. So current is flowing like this, in this, going into the plane of board at the top, coming out of the board at the bottom here, at this portion. So cross-sectional view of this we can show. So going in means X mark we can show. The current is entering into the board, X mark. Okay, so like this. And here dots we show means current is exit or coming out of the plane of board, like this, cross sectional view of this. And now the magnetic field direction of current is like this. So curved fingers, how to apply the right hand rule? The current carrying solenoid or coil is held in right hand such that the curved fingers in the direction of the current, curved fingers in the direction of current, then the outstretched thumb gives the direction of magnetic field. So this is the direction of magnetic field. So outward means field lines will be like this. Okay, so magnetic field. So this will become like north or south pole. Field is entering and field is coming out here. So this end of the solenoid behaves like a north pole. This end behaves like south pole. Okay, the magnetic field lines here. Okay, field lines will be like this, and the field lines are closed loops here actually. Okay, magnetic field lines are closed loops without any break. So we have to continue like this. Okay, so continuous. They are closed loops. Unlike in electric field lines are only one-sided. Positive charge to negative charge, or positive charge to infinity, infinity to negative charge. Whereas here, if you start from a point, you have to reach that point in case of magnetic field lines. Okay. So this is the diagram for the solenoid. Solenoid consists of a cylindrical tube on which a large number of windings are made. Assume that this is a cylindrical tube. Okay. Now I take insulated copper wire, thin copper wire with insulation, thin insulation with it. So what is the requirement for that insulation? That is, even if the wires are in touch, in contact, but they no current flows from one wire to another wire. So very thin insulation, copper insulating material coated on that wire. Okay, in the windings and all, such a technique is used in the windings of motors, say water pump, all that, in the fan and all. The thin wire will be there, and the thin wire is also coated. Every turn of every wire is coated, means the one turn and another turn touching also will not pass the current. Current will not flow from one to another. There is a physical connection, physical contact, but there is no electrical connection between one turn and another turn, one loop and another loop. So there is no flow of current from that, and only through that length the current flows. Okay. So like this is the arrangement, and the magnetic field here inside the solenoid at this point, it is given by B equal to, at this point the magnetic field here is at the inside the solenoid. Magnetic field inside the solenoid, magnetic field value. Okay, magnetic field B, magnitude of magnetic field B equal to, it is given by the expression mu naught Ni. This is the expression for the magnetic field due to solenoid inside it. And at the ends of the solenoid, the field is mu naught Ni by 2 divided by 2. That is not mentioned in the syllabus. Only inside the solenoid, at the middle of the solenoid, the magnetic field is given by this expression. Now what is N? N means number of turns per unit length. Suppose this solenoid has a length L and it has got number of turns, say n number of turns. Then we can say n equal to n divided by L. Okay. For example, if there are 200 turns, there is a small solenoid, 200 turns are made. 1, 2, 3, 4, like that. 200 turns are there from one end to another end, wounded closely. Then the value of small l, length is, say, for example, I am telling, length is some 20 centimeter. Okay, 200 turns are there and 20 centimeter length. So 20 centimeter length, when you write in meter, it will be 0.2 meter. Agree? So 0.2. Okay, now 200 by 0.2, multiply 5 here, 200 into 5 is 1000. 0.2 into 5 is 1. Okay, so it is n value is 1000 turns per turn or unit length. Okay, per meter. Here we can write per meter. There are 1000 turns in 1 meter length of the solenoid. That is the value of n. And mu naught is a constant. Okay, so if the current is, say, 2 ampere, a current of 2 ampere is flowing through this solenoid, then what is the magnetic field in such solenoid? If n is 1000, very simple, B equal to mu naught N. Substitute the value. Mu naught is 4 pi into 10 raised to minus 7. Then n value is 1000. I have taken as example 1000 it is, and current is 2 ampere. Okay, so 2. Now you have to multiply. This is 8 pi into 10 power minus 4 Tesla. So this is the magnetic field produced by a solenoid having length 20 centimeter, 200 turns in it, carrying a current of 2 ampere. So this is the formula which I use to find the magnetic field produced by a solenoid inside it. Here, magnetic field is uniform inside the solenoid, and outside we take approximately 0. There is a magnetic field almost 0. It is negligible, not 0 actually, approximately 0 or negligible value. Now I have another device, toroid. Okay, another device, toroid. Okay, toroid is a ring-shaped object. Okay, so which has a coil like this. Suppose if you take the solenoid, long solenoid, and fold it to make a ring shape. Okay, so that is what toroid is. So toroid is a circular ring-shaped object on which a large number of thin insulated copper wire is wounded. Okay, insulated copper wire is wounded. From one end the current end. So now if I take the turn like this, okay, so then I make the winding here. Okay, like this. I make the windings here. Okay, so the windings are made like this, like this. Okay, so I can show the windings like this. I do from this side. Okay, so windings are made here like this. It is a uniform, it produces uniform magnetic field inside it. Again here in toroid also, the magnetic field is produced only in the tubular region, and outside the toroid, these are the turns, windings. Okay, so here one end current enters to the wire, another end it flows out. So this carries a current like this. Okay, current is flowing on the windings, and here current is coming out from this. Okay, so this is all about the toroid, and we have the magnetic field. So here magnetic field is 0, and here outside also magnetic field is 0. Then where is the magnetic field? Magnetic field is there only inside the toroid, tubular region. So for example, if I take a cycle tube, okay, so cycle tube, if you make windings on that tube, or take a small ring and make windings on that, pass current through that wire winding. So then it produces magnetic field in the tubular region, wherever coil is there, inside the coil. Outside that, magnetic field is negligible or 0. So a toroid is simply nothing but a long solenoid made joint to make one ring. Okay, if you bend the solenoid into circular form and bend it, one end and the other end of the solenoid is bent, joined together. So then it becomes a toroid. Okay. So it is a tube ring shaped object, and windings are made on the ring form. Okay. So again same here, copper, insulated copper wire is wounded very closely. Here space is shown, but not necessary actually. They are made very closely. It is just to represent the current, and I made space actually. The windings are one over the other like this. It comes very close windings, both in solenoid as well as toroid. They are physically in contact, but electrical connection is not there from one turn to another turn. Current does not flow directly. It will flow through the length, okay, through the wire. Okay. So now magnetic field in this region, outside the toroid field is 0. In this region, in the hollow region here, what we can see, there is magnetic field. But in this region, inside the tubular region, there will be magnetic field, and the magnetic field inside tubular region, if I take the radius BR, the average radius of the toroid be smaller, then it is mu naught Ni. I take a mu naught Ni divided by 2 pi r. Okay, so this is the magnetic field in the tubular region of the solenoid. Here, tubular region means only this region of the toroid there is magnetic field. Here magnetic field 0. Outside also magnetic field is 0, but only in this tubular region. Like in a bicycle tube, the air is there, pressure is there. Air is there with the pressure only inside the tubular region. Outside and inside, air is there, but it is negligible. Same way here also. Here field may be there slightly, but it is negligible value. Here also negligible value. Only in the tubular region there is enough magnetic field, and that magnetic field expression is mu naught Ni by 2 pi r, where N is the total number of turns in the toroid. Total number of turns in the toroid. I is the current carried through the toroid, and R is the average radius of the toroid. So this is the expression for the magnetic field expression. Magnetic field produced by the toroid. So solenoid and toroid are the two devices which produce magnetic field. Both of these instruments used to produce uniform magnetic field. Both of them produce uniform magnetic field. That means this value of magnetic field is same everywhere inside. Same magnetic field everywhere. So uniform magnetic field is produced by the toroid. Okay, so these are the two devices which are used to get the uniform magnetic field. Okay, these are practical applications. In some devices we need the magnetic field, uniform magnetic field. In such cases we use these two devices to produce the magnetic field. So that's all about this class. Okay, that's it.